Welcome to lesson 7.3. Today we're going to go over similar right triangles, and we're going to learn 3 new theorems as well as review the geometric mean, which we learned earlier in chapter 6. So the first theorem is theorem 7.5. This theorem states that if an altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So just kind of to refresh your memory, we don't have to draw an altitude on a right triangle because we know its height. However, we certainly can draw an altitude. So we're going to draw the altitude CD to the hypotenuse AB. So there's our altitude CD. And what this theorem states is that the two triangles formed are similar to the original triangle and to each other. So we have 2 new triangles that we formed, and we're going to call those out a little bit. So we've got triangle CDB and triangle CAD. And I've just separated those out. Those are just same triangle. I just kind of broke them out from that bigger triangle ABC. And what this theorem says is that all 3 of these triangles that you see in front of you are similar to each other. So let's write out those similarity statements. And I've got them written in color-coded here, so that way you can help see what corresponds with what. So remember, in a similarity statement, you have to keep your corresponding parts of the triangle written in order. So let's take our triangle CBD. That's going to be similar. So CB is our hypotenuse right here. So CBD is going to be similar to triangle ABC, and we've got our hypotenuse written first in that triangle. And then we also have triangle ACD is similar to triangle ABC. And lastly, triangle CBD, our blue triangle right here, is similar to triangle ACD. So these 3 triangles are in fact similar to each other according to our new theorem, as long as we draw the altitude from the right angle down to the hypotenuse. Okay, let's move on to the next concept. So remember, from chapter 6 we talked about geometric means. Just in case you don't remember it so well, I know you guys know it very, very well, right? You don't forget anything, but just in case, let's quickly review what the geometric mean is. So remember, the geometric mean is a number x such that a over x equals x over b. We can also write this as the geometric mean is a number x such that x squared equals ab. This number x is your geometric mean. Geometric mean can also be applied to triangles. You should have guessed that by now. Anything that we're doing in geometry pretty much can be applied to triangles. So let's go ahead and apply it to triangles. So we've got our triangle, our right triangle right here, ABC. If we draw the altitude CD like we have here, we can use that as a geometric mean. And specifically, since CD breaks up our segment or our hypotenuse AB into 2 segments, segment AD right here and segment DB, it is the geometric mean between those 2 segments. So it broke up our hypotenuse into 2 separate segments, and it's now the geometric mean between those segments. So BD, which is the smaller segment here, over CD, which is our altitude, equals CD over AD. That means that they have the same proportion to each other. Okay, we actually have a theorem that goes over this specific concept. So theorem 7.6, the geometric mean or the altitude theorem, says that in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into 2 segments. That's exactly what we just did on the previous slide. So specifically, this theorem states that the length of the altitude is the geometric mean of the lengths of the 2 segments. Okay, so let's just review again what we went over on the last slide. So here we've got a right triangle, and we've got an altitude drawn from the right angle to the hypotenuse. That's segment CD. This theorem says that the length of the altitude is the geometric mean of the lengths of the two segments. So that means the geometric mean is going to be in both equations. Here's our x, CD, you see it both here, and BD over CD is going to have the same proportion ratio as CD over AD. And we're going to put this into an example in a couple of slides here. But before we go into an example, we have one last theorem that actually applies the geometric mean to both legs of the right triangle. So let's go into that theorem next, and then we're going to put these into examples. Okay, so we're on our last theorem for this lesson. Theorem 7.7. It's very similar to the geometric mean for the altitude theorem, but as I said previously, this is with the legs. So the theorem starts out just the same. It says in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. We've seen that. So now specifically what this theorem states is that the length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. So remember, our altitude divides our hypotenuse into two segments. And let's redraw this triangle. So we've got triangle ABC over here with altitude CD. So we have this altitude drawn into two segments, segment AD and segment BD. These are two separate segments here. What this is saying is that the length of each leg of the right triangle is the geometric mean. So that's going to be what's repeated in our equation. And it's the geometric mean of the lengths of the hypotenuse itself and the segment adjacent to that part of the leg. So we have a couple of equations here. We've got two separate equations here. We've got AB over CB. So remember, AB, that's our hypotenuse. And we expected that to be in here because it says right here that the length of each leg is the geometric mean of the lengths of the hypotenuse and the segment adjacent. So we've got our hypotenuse AB, which is going to show up in both equations, and then CB is one of the legs of our triangle ABC. Right here, we've got a leg right here. So this is one possible leg, and then we also have leg AC, which we're going to see in our other equation. So CB is the leg that we're using in our first equation. That's the geometric mean between our hypotenuse and the segment of the hypotenuse that is adjacent to the leg. So if this is the leg that we're using, CB, the segment that's adjacent to this leg that is part of the hypotenuse is segment DB right here. And that's exactly what we see in our equation. So these are proportional to each other, or proportionate to each other. So AB over CB equals CB over DB. And if we were to use our other leg, so leg AC instead, the segment of the hypotenuse that is adjacent to AC, here's our leg AC, is AD right here. So that's what's going to be in the equation instead. So we still start out with a hypotenuse. Hypotenuse over the leg equals the leg over the segment of the hypotenuse that's adjacent, which is AD. So we have AB over AC equals AC over AD. Okay, I know that's a lot of variables and a lot of things in theory. So let's actually put these into a couple of examples. And then tomorrow in class, or when I have you guys in class again, you'll be able to go over these with your classwork. Okay, so the first thing that we're going to do is we're going to write a similarity statement and complete the following proportion. So we have three different triangles here. First, we need to write the similarity statements. So we have from our very first theorem that we learned today, we know that triangle ABC is similar to triangle. So if we go A, B, C, we can say that that is similar to triangle C, B, D, which is also similar to triangle ACD. 'D. we have three different triangles that can be divided up here when we've drawn the altitude from the right angle. So here is our similarity statement. Okay, let's clear that part out, the similarity statement out, and let's solve our proportion now. So we've got the proportion AD over blank equals CD over BD. So let's take a look at our triangle here and see what exactly they're looking at. So we've got segment AD right here over something equals CD, which is our altitude, over BD. Okay, so this looks very similar to the theorem that we learned a couple of slides ago, which states that CD is the geometric mean of the two segments that are divided by the altitude, segments AD and DB. And in fact, we can apply that theorem to this proportion and say that AD over CD equals CD over BD. So our answer to this proportion is CD, and that's applying the theorem that we just learned a couple of slides ago. All right, we're on our last example now. So if AD equals 4 and BD equals 5, what does CB equal? Let's label everything that we've got and figure out what theorem we're going to use. So AD equals 4, BD equals 5. What does CB equal? So we've got two segments that are divided by the altitude, and we're looking for the length of the leg. So that means that we're going to use the last theorem that we just learned, which is the geometric mean of the legs theorem. And if you remember, that theorem said that the hypotenuse, so AB, over one of the legs, and in this case we're going to use CB because that's the leg that we're solving for, equals that leg divided by the segment of the hypotenuse that's adjacent to that leg. So here's the leg that we're looking at right here. So therefore this segment right here, DB, would be the segment that's adjacent to that. So that's our proportion. We've got our proportion set up. Now we just got to plug in the right numbers. So AB, that's actually going to be 9 units because that's this entire length of the hypotenuse. So that would be AD plus DB. So that means that we have 9 over CB equals CB over DB, which equals 5. Cross multiply, and we get CB squared equals 45. So the length of the leg, CB, is approximately, if we take the square root of 45, that's 6.7 units. And there's your answer. You were able to solve the length of the leg using the last theorem of geometric means. Okay, that's it for today. I hope you enjoyed this and look forward to any questions that you guys might have in class later. Have a good one. Bye-bye.